Thanks.
Thank you very much, and thank you for the kind invitation. So I will briefly introduce what eROSITA is and describe the instrument and our observational program, and provide some limited overview of some scientific highlights from the Earth-Sky survey. There will be another talk after your lunch break from Emmanuel Arti, who's also a member of the eROSITA team, a cosmologist that will focus on cluster cosmology. And of course, in a sense, the only cluster cosmology slide I'm going to present is this one, because cluster cosmology was indeed the main scientific driver behind the design of eROSITA. Very simple, I'm sure you are well aware of this. Here is just a very simplified explanation of why you would build an X-ray telescope to do cluster cosmology. And it's encapsulated in this very old picture on the left, which is from a simulation of almost 30 years ago now, of dark matter-only particles sliced at different redshift, showing the filamentary large-scale structure. And in this particular figure, what you see are different cosmologies, and it doesn't really matter right now which ones, shown at different redshift, all tuned to reproduce some basic statistic, zeroth order statistics of clustering at redshift 0. And here you see how they look very different when traced back in time. And in particular, we are interested in the distribution of the nodes and knots in this large-scale structure, the biggest halos that host the biggest clusters, because, of course, they are rare, exponentially rare, and because of that, they are also exponentially sensitive to the growth of structure. Here you see on the right, in the bottom right, an old review plot from Rosati et al. 2002 that more or less give another representation of this I just told you. This is just the simplest statistic you can build, counting halos. So this is the number of halos bigger than a given mass, than a certain mass. Here in particular is the biggest big cluster scale mass, 5 times 10 to the 14 solar masses, normalized to their redshift 0 number density as a function of redshift for different cosmologies. Here, of course, some of these have been long ruled out since 2002, but here, notice that this is a logarithmic scale on the y-axis. So essentially, the experiment we were after was a counting experiments, constrain the mass function of the biggest structure in the universe at moderate to high redshift. And of course, we use an X-ray telescope because a signature of cluster is their hot extended X-ray intercluster medium, so tens of millions of degrees. And so the instrument we built was designed to have a point spread function not as good as the best X-ray telescope that we've ever built, like Chandra, but good enough to distinguish spatially an extended cluster, a big cluster extended in the sky from point sources, and also to be sensitive enough to detect large number of clusters so that you can beat down statistical errors in the study of the mass function. So roughly speaking, this was the design driving science of eROSITA, but I will refer to Emmanuel's talk for what we actually have accomplished with this telescope in terms of cluster finding and cluster cosmology. Okay, but then based on this very simple motivation, the telescope we built is pictured here on the left. You see on the left and right some picture taken in the MPE lab in the construction phase about 6-7 years ago. So eROSITA is actually an array of 7 identical X-ray telescope. Here you see the entry side on the left. They are characterized by lightweight mirror replicas, so the same technology of XMM Newton. So with this, you can assemble quite a large effective area. And so the effective area of eROSITA is the largest at soft X-ray energies of any X-ray telescope ever flown. And we have also combined this with a fast telescope design that allow a large field of view. which is unprecedented in again in X-ray astronomy, almost unprecedented. We have about 1 degree diameter field of view. The optics deliver relatively good spatial resolution. On axis, our half energy width is about 18 arc second. When you average over the field of view, is about 30 arc second. This allows us to position point sources to about 5 arc second, which is at the depth of the survey, in most cases, sufficient to have a reliable identification of the optical counterpart for any astrophysical source. We put a lot of effort in building baffles to reduce stray light. And on the right-hand side, you see a picture of the focal plane where we have 7 identical CCD cameras, 1 per telescope, of course. So in total, we have about 1 million pixels over the 7 cameras. The pixels are relatively big, 9 arc second in size. They are, of course, matched to the size of our PSF. The advantage of the camera here, you see a picture of the one camera taking PSF images in our lab, is that the entire camera is exposed. There are no chip gaps, and we have a frame stored, so we don't have out-of-time events. This increase our efficiency in detection. And as you probably are aware of, because we work in low photon counting regime, we are able to measure the energy of each incoming photon. So effectively, X-ray CCD images are like integral field units because we can build a spectrum. Of course, provided we get sufficient photons for a source, we can build a spectrum because we measure the energy of each source, and our spectral resolution is like a poor grism. It's about 80 electron volt at 1.5 kV. So roughly speaking, resolution 20. This is just to hammer home the message that eROSITA is the largest X-ray telescope. This is now a field of view average effective area as a function of energy of eROSITA in red compared to other X-ray big telescopes that are currently on past operating. In blue is XMM Newton, which is the largest observatory in space right now. And then in green, for example, you have Chandra. And the energy range between about 0.2.3 kiloelectron volt to 2.3 kiloelectron volt, where we have absorption edge, is the region of our maximal effective area. And in this range, the effective area is comparable with XMM Newton, as I mentioned before. When you then compare the field of view of XMM Newton with the one of eROSITA, here you see their representation on the left, and Chandra is even smaller than that, then you realize that the grasp, so the product of effective area times survey speed, is maximal for eROSITA. So if you want, eROSITA is the fastest X-ray survey telescope that was ever built and operated. Beyond how fast you can survey the sky, we have also developed an observation mode in which you don't need to point at stare to move the telescope in fixed pointings, but we can scan a large swath of skies, either in continuous scanning, as in the survey. I will tell you in a minute how we did it, but also you can cover any rectangular sky area of up to 150 square degrees in this raster scan mode. So this allows us to create very large scale images with very uniform exposure. Here you see an example on the right, which is an X-ray image in the soft X-ray energy range of emerging cluster system of several square degrees. And this is nice because it allows, for example, in this particular case, to trace not only the cluster merging system, but also the surrounding large scale structure. Here you can see a few extended blobs. These are all groups that are at the same redshift of this triple merger cluster system that we all detect in a single eROSITA image. And this is the same field exposed during our performance verification phase, now in X-ray false colors. And most of the, essentially all of the point sources are background AGN, but most of the extended sources you see here are groups and clusters that are part of the same large-scale structure. So it's a fantastic machine to study large-scale structure, in particular to image large-scale structure in the local universe. So this machine was launch within the spectrum Röntgen gamma satellite into a large halo L2 orbit. Here is the profile of the orbit. And so this is the first X-ray telescope operating at L2. L2 is good because it provides thermally stable environment, thermally stable environment, and so it's optimal for high efficiency survey work. Being the first telescope at L2, we have also, for the first time, probed the particle background at L2, which is the interaction of the solar wind with the tail of the Earth magnetic field. It's called magnetotail. And the good news is that the background, at least in the early phases of the mission, close to solar minimum, was very stable, much less variable than XMM and Chandra, which are in highly elliptical low Earth orbit. Here you see a comparison of an observation that we did of the same source, part of the sky with eROSITA and XMM Newton, and the eROSITA background is the red, and the XMM Newton is the blue in 3 different energy beams. The background itself is a bit higher than what we have predicted before launch. This has to do mainly with the not accurate instrument mass model. But in general, we can say that the particle background is now relatively well understood at L2, thanks mainly to eROSITA. A few details about how we calibrate the instrument to give you an idea of the performance. These are 2 images that show X-ray spectra of sources dominated by emission lines with very high photon counting that we use to calibrate the energy response of our detectors. Here on the left is a supernova remnant, 1E0102. This is a standard X-ray calibrator because its spectrum is soft. At low energy, is essentially a collection of a plethora of partially ionized emission lines. Of course, at our resolution, we don't distinguish all the detail of the lines, but we can clearly, because the source is very bright, centroid the line very accurately. And so this allows us to reduce our energy calibration, so the uncertainty with which we can assign an energy of an incoming photon, to about, let's say, 3 electron volt or smaller, which is really small, comparable to calorimeter accuracy. But of course, then the light spread function is much bigger than that. And here you see similar outcome. This is now a spectrum of the background, or actually the foreground. This is diffuse emission from the Milky Way integrated over an area of about 100 square degree. And in that particular case, the temperature of the plasma is a bit warmer than the supernova remnant. And so in fact, the diffuse sky at half a keV is dominated by oxygen 7 emission line from the CGM of the Milky Way. And in both cases, we have similar energy calibration accuracy. And this is just to show that our PSF model is a good representation of our PSF. This is the PSF that we obtain on sky by stacking stars and quasar point sources. So we can extend we can model quite accurately the wing of the PSF up to several arc minutes away from a source by combining several sources together. And here you see a comparison between pre-flight and in-flight measurement of the half energy width. I told you already about 30 arc second here in the second row. And on the right-hand side, you see a comparison of the PSF of the 7 telescopes, just to see how close to each other they are. And so overall, quite well under control also the PSF, which is very important to model extended emission-like clusters. And then finally, about flux calibration, this is a little bit more complicated because it's very hard to calibrate effectively the effective area on ground because you never reproduce the source at infinity that you have in space. But by comparing, for example, a large number of sources between eROSITA and XMM in a large catalog, of course, you have a lot of variable sources that scatter out. But if you look at this red distribution on the right-hand side, these are the brightest sources, ratio of the flux measured by eROSITA and XMM Newton, and you see that the mode of this distribution is very close to unity. So we think that our fluxes are accurate, or at least are consistent with XMM Newton to better than 10% in the soft energy range. In the hard energy range, where our effective area is smaller, this accuracy is less precise. And this may have still some effect that we are working on in terms of our ability to measure temperature of hot clusters, for example. Okay, let me move now to programmatic, what we have done, so that I can show you some scientific highlight now. So the telescope was launched, the SRG was launched in July 2019. And by the end of 2019, we had completed our commissioning and calibration and performance verification phase. The data taken in this period were released already almost 3 years ago in the early data release in summer 2021, including several individual fields and the EFET survey, which was quite competitive X-ray deep image of 120 square degree that we have extensively used to do science and also to validate our strategy for source detection, identification, redshift measurement, follow-up, and so on. Then in December 2019, we start the main program of our science program. So there was an all-sky survey. And eROS is the acronym of eROSITA all-sky survey. This will be appear frequently in my presentation. And in 6 months, we completed the first all-sky survey, and the data of this eROS-1 all-sky survey were released early this year in the DR1 on January 31st of this year. And we were planning to do this for 4 years to complete 8 all-sky survey. It takes about 6 months to complete a full survey of the sky. But we suspended our scientific program in February 2022 following the invasion of Ukraine. As this was a German-Russian cooperative program, this cooperation has been suspended. At the moment, eROSITA is in safe mode, so it could be restarted anytime if the conditions allow. But at the moment, we haven't taken any data since 2022. So we have about 4.4 all-sky survey data. Right? I will show you, this is a very rich data set. This is some numbers out of this all-sky survey. The sky is covered quite fast, and so we reach an average exposure of about 800 seconds over most of the sky. And due to the geometry of our scanning load that I will show you again later, close to the ecliptic poles, our scans intersect, and so we have much deeper exposure, exceeding actually our confusion limit. Because of the few background flares and some flexibility mission planning, we don't have any gap. So whenever we had to interrupt observation due to orbital maneuver and so on, we could always close any gap that was left in the survey. So the skies cover uniformly and without gaps. In total, we have detected of the order of 1.5 billion calibrated photons in the 0.225 keV energy range. And these were extracted out of a relatively small volume of telemetry. So the data are highly compactified and compressed. For the X-ray aficionados, these are some numbers. The single pass sensitivity in the soft energy band between 0.2 and 2.3 keV is about 5 times deeper than the ROSAT all-sky survey, reaching of the order of 5 times 10 to the minus 14 Hertz per second per square centimeter sensitivity. In the hard energy range above 2.3 keV, due to the drop in effective area, we have a much shallower limit, about an order of magnitude shallower. And then if you stack 4 surveys together, that allow you to reach down in flux to about 2 times 10 to the minus 14. So with these sensitivities in eROS-1, over just half of the sky we have analyzed, we have detected almost 1 million point sources. And this number is kind of a milestone because doubles the number of known X-ray sources before eROSITA was launched. In 50 years of history of X-ray astronomy, about 1.2 million, 1.3 million sources were known before eROSITA. And in the preliminary version of the stacked catalog that we still have not released, but we are working on it, we have about 3 million point sources over half of the sky. And then we have of the order of, we are close to 100,000 extended sources. And right now, preliminary analysis of the cluster content of the eROS-4 sky gives a number of the order of 45,000 confirmed clusters. Now let me take 1 minute to show this beautiful animation, which is a tour. So now we are showing in the X-ray photons from eROSITA, color-coded by the energy, projected onto a sphere. So it's only half of the sky. This is the part the German consortium have the proprietary access to. And here you see this image is in galactic coordinates. So you see the galactic plane on the horizontal line, and plenty of famous sources and structures throughout. So now we are moving towards the galactic anticenter. This bright source is the crab. It seems extended just because it's so bright that it fills the PSF. Now we are moving to the extragalactic parts of the sky. All this reddish emission is CGM from the Milky Way. And on the left-hand side, you see the North Polar Spur, and the bright source at the center is the Virgo cluster. We now move to the southern galactic cup, where the Magellanic Clouds are. So LMC is very prominent in eROSITA, full of hot gas energized by supernova remnants. And here now we are moving back towards the galactic center with all this detailed structure of the obscuring gas and dust that absorb the softer X-ray. And that's why you see mostly bluish radiation in the galactic plane. And the bright source at the center we just quickly skim over is the Vela supernova remnant. So it's a very rich and beautiful sky that we are uncovering with eROSITA. Okay, in terms of statistics, breaking down in approximate way all these hundreds of millions of calibrated photons, this is for ERAS-1 only, for the first pass. So in 6 months, we detect mostly, so the majority of the photons, as you might have guessed from this image, this structured reddish, yellowish emission. This is what we call diffuse foreground, that we tentatively can separate in 3 main components. One is the large-scale CGM or ISM of the Milky Way. Then we have much more local effect. The SWXCX is the solar wind charge exchange that dominates a very, very low X-ray energies. And similarly, warm emission comes from the so-called local hot bubble. This is a million-degree, 100-parsec bubble, probably inflated by past supernova in which the solar system is embedded. The second largest component is the cosmic X-ray background. This is actually unresolved emission from sources at cosmological distances, mostly AGN, but a small fraction also from groups and clusters of galaxies. And this large number of unresolved sources can somehow statistically be recovered by stacking experiments. This gray FWC, this is called filter will close. This is what we get even when we close the filter of the detector. So this is the genuine particle background due to interaction of cosmic rays and solar wind with our instrument. So this is really the unwanted part of the measurements. And the individual sources, point and extended, are these red and yellow wedges. Only about 10% of all the photons cannot be attributed to individual sources. All the data, the catalog, in fact, all these photons, one by one, can be retrieved in our data release 1 web pages, where we release not only the events, but also the software, the calibration database to reduce the data, the attitude file, the exposure maps, and the catalogs, of course, and some properties of individual sources like spectra and light curves. Okay, this is now a little bit an animation that shows you the mechanics of the All Sky Survey. Now, it's again only half of the sky center on the German half in galactic coordinates. And here you see how the survey progressed. This is about 6 months worth of data in just a few seconds. Essentially, what we do is we progress by great circles which all intersect in the south ecliptic pole or in the ecliptic poles. And this image is not corrected by exposure. So you see this very bright central source is the high exposure close to the ecliptic pole. So it takes about 6 months to cover the whole sky. And this gives me the opportunity to tell you a little bit about the time domain aspect of the eROSITA survey now. So there are several timescales we are sensitive to. This is interesting because it's unprecedented large volume of data in time domain for an X-ray survey that can be and has been used to detect transient on different scales. So the fastest time scale we can resolve is about the readout time of our CCD, the readout cycle actually of the CCD. So we read the CCD after every 50 milliseconds. So this is the fastest variability we can ever detect. But we haven't really detected anything at those time scale yet. Then in this continuous scanning mode, a source is never static in the sky. It passes through our field of view, and given the scan speed and the size of the field of view, it takes about 40 seconds for a source to pass in our field of view. And this is the unit observation time. We call it visit. So this is the our unit of exposure, if you want. Then scan, a full 360-degree scan takes 4 hours. And after 4 hours, the same source, because the scans are highly overlapping, the same source will re-enter our field of view, and we will have a second visit. And typically, a source takes 1 day to enter and exit our field of view permanently. And so we have about 6 visits separated by 4 hours for every source in the sky. And this map on the right now shows half of the sky color-coded by the number of visits after 3 all-sky surveys. So you see that most of the sky is red-orange. This corresponds to about 18 to 24, 6 to 8 visits per source in 1 day. And then the blue dark part is the south ecliptic poles, and here we go up to hundreds of visits in a small area around the ecliptic poles. And this pattern essentially repeat every 6 months. So one source gets 6 visits in 1 day, and then another 6 visits after 6 months. And this allows to trace phenomena on this time scale of hours, days, and months. In particular, the 4 hours time scale done so systematically was very rich of new discoveries. For example, in a Nature paper about 2 years ago, we were lucky enough to detect a nova in its fireball exploding phase, just because we passed over a source and we detect very bright emission that saturates our telescope, but the source was absent 4 hours before and 4 hours after. So we could constrain very accurately the timing within 8 hours of the explosion. And this turned out to be the early phases of a bright nova, visible in naked eye with optical telescope, that found this nova only after the X-ray discovery by eROSITA. And so with eROSITA, we are able to put some constraint on the black body temperature of this expanding fireball, and so also confirm some of the nova theory that would predict this X-ray flash that was never observed before. A second major discovery that we made, thanks to this cadence of 4 hours, was actually 4 quasi-periodic eruptors. These are really fantastic objects. With eROSITA, we only get candidates. So we are searching for extragalactic sources in the nuclei of nearby galaxy that appear, that are bright in a visit and then disappear in the following visit, and they're bright again. And then we follow this up with XMM Newton or nicer. So these are the first 2 we discovered in this Nature paper by Arcodi et al. In 2021. These are not the eROSITA light curve. These are the follow-up light curves. But here you see nuclei of galaxy that reach Seyfert-like luminosity. In this particular, in the top, it's 10 to the 43 ergs per second at the peak. In the bottom, 10 to the 42 ergs per second at the peak. So it reached AGN-like luminosity in a burst that lasts only a few tenths of minutes or a few hours, with recurrence time ranging from 2 to 10 hours or 20 hours. So these are really fascinating phenomena. We are now, thanks to eROSITA, we can build some statistics because we can model our selection function very accurately. So this is the first luminosity function of QPE ever published. And this on the right is the rate. And the comparison with the QPE rate, which is in red, show that TD rate in red, QPE are rarer, are about 1 in 10 or 1 in 100. And the connection between these 2 populations is now actively studied by theorists. I mentioned tidal disruption events. This 6 months time scale is a very good time scale over which we can detect bursts from galactic nuclei that don't show any AGN signature that could be associated with TDE. And Yulia Grotova is completing a paper that presents the first catalog of TDE of about 300 X-ray selected TDE candidates, out of which we have done intensive follow-up program of the best 25. And these are golden, also called golden sample, for which we have X-ray spectroscopy and optical spectroscopy, so that we are 100% sure these are tidal disruption events. And this publication will come out soon. Okay, I'm going fast now. I should finish in a few minutes, but let me mention the first major discovery of eROSITA when we combine the two halves of the first all-sky survey sky of the German and Russian team in 2020. We notice, looking at the image in the energy range between 0.6 and 1 keV, that in the southern hemisphere, a bubble-like feature that here I'm tracing with my cursor mirror the North Polar Spur. There was a well-known structure found by Rosat, whose location was always controversial, either a galactic center feature or a local supernova. But the symmetry between the north and south that eROSITA discovered made us believe that what we are actually looking at is a bubble-like system that we called eROSITA bubbles in this paper by Predel et al. In 2020, also due to the similarity with the Fermi bubble. Here you see an image in which in cyan I show again the eROSITA 0.6 to 1 keV sky, and in red is the Fermi emission above 1 GeV with the Milky Way Milky Way unresolved emission, and this lobe-like north and south bubbles that Fermi discovered about 15 years ago. And the eROSITA bubble seems to envelope the Fermi bubbles. And so in our discovery paper, we made a toy model associating the Fermi and eROSITA bubble to a model similar to a hot wind, like a solar wind, if you want, in which the Fermi bubble represents the shocked hot wind. Their edges, a contact discontinuity between the hot wind and the shocked ISM, and the outgoing edges of the eROSITA bubble are the outgoing shock front. If you take some basic measurement of the temperature of the ISM that we have from XMM Newton before, now also for eROSITA, you can derive an energetic of about 10 to the 56 ergs that are needed to inflate this system of bubbles, and an age which is very uncertain, but must be at least a few million years, up to about a few tens of million years, which then put together gives an energy release rate of about a few times 10 to the 41 ergs per second that must have happened probably at the galactic center a few tens of million years ago. And this is difficult to do for supernova-driven, for starburst-driven event, but not impossible. So it's still not exactly clear what is the prime origin of this energetic event at the galactic center, but probably some past AGN activity would be most favored. And now what we are working on is to take full advantage of the spectroscopic probability of eROSITA to study the interaction between the bubbles and the CGM. These two maps now show the diffuse emission in the oxygen 7 and oxygen 8 band. Essentially, we only take a very narrow range in energy, subtract the cosmic X-ray background, and measure and make this map. Then you can combine this map into a ratio, which is temperature-sensitive ratio. So the ratio of 07 to 08 in a single temperature plasma is directly proportional to temperature. And here we are color coding this ratio map by this what we call pseudo temperature, because of course the interpretation of it as a temperature relies on the assumption of a single temperature plasma. And so you see that the eROSITA bubbles are hotter than the rest of the CGM, and there is cold gas here highlighted in this green, by these green markers, soon outside of the bubble. So there are clearly some pushing out of colder gas by these expanding bubbles. Another puzzling feature that we found is that if you look at the unperturbed part of the CGM, so farther away from the bubbles, there is an asymmetry in the temperature distribution of the north and the south. So the difference is about 12%, and it's quite significant. It's very significant. Here you see the distribution of pseudo temperature in the north, in this northern and southern region. And this is at the moment unexplained. Okay, finally, a few words about the catalog. I told you that this is a plot that shows the number of sources in any X-ray catalog since the history of X-ray astronomy from the 70s to now. And eROS-1 covers only half of the sky, so that's why it's only half-filled circle, and produce a catalog of almost 1 million sources, which is the largest that we have at the moment in X-ray astronomy. What we have done is to generate two separate catalogs. The main one detecting sources in the sensitive soft band, and this, of course, is the largest catalog with 900,000 sources. And then we have a hard band selection. So we essentially run our source detection above 2.3 to 2.3 kV. And so we can detect hard sources in much smaller number because of the lower sensitivity, which are interesting, however, because it less biased by intervening absorption. And this plot shows the counts distribution of the main catalog on the left and then the hard catalog on the right. Of course, most of our sources are detected with only a handful of counts. You see here there are less than 10 counts for hundreds of thousands of sources. And you need of the order of 100 counts to start doing proper spectroscopy. So most of our detection are very poorly characterized by the X-ray themselves, and the follow-up programs are very important. Of course, in order to do follow-up, you need to identify the source counterparts, and that's why the astrometry of eROSITA is very important. This plot on the right shows the statistical positional uncertainty as a function of the detection likelihood, which is approximately the number of counts. Of course, very bright sources with a high detection likelihood can be positioned to a couple of arcseconds. The median positional error is about 4.3 arcsecond. And we have systematic uncertainty to add in quadrature to this, which is less than 1 arcsecond. Our pointing stability of the telescope is very good. This is a plot that shows how this non-uniform exposure map translates in a non-uniform flux limit. So if you ask what is the flux limit of the eROSITA All Sky Survey, this is not an easy thing to, not a question that have a simple answer. There is a distribution of flux limit depending how deep the exposure is. Close to the south ecliptic pole, we can go much deeper. And this histogram shows the distribution of flux limit in pixel. The median is about 5 times 10 to the minus 14. This is the number I quoted before. And this is the equivalent completeness fraction as a function of input flux based on accurate simulation of the detection process. So you see that most of the sky's exposure have exposure of about 100 seconds. So this will be this blue line. And so above 10 to the minus 13, our completeness reaches more than 95%. And below 10 to the minus 14, we only detect, we are extremely incomplete. Okay, if any of you is interested in stellar astrophysics, we have a very large number, almost 100,000 coronal emitting stars. These are main sequence stars that, like our sun, produce X-rays in their corona, sometimes in a flaring fashion, sometimes in a stable fashion. And Gaia is very good because it's deep enough to identify essentially all of them, given what we know about the typical X-ray to optical flux ratio of stars. And this is a so-called, so we can start with these numbers, really doing population study of X-ray emitting coronal stars. And this is important because these stars trace, the strongest X-ray emitters trace youngest, fastly rotating magnetized corona. And this has important implications for stellar-planet interaction, but also for stellar physics itself. And this is a sort of X-ray Hertzsprung-Russell diagram in which, as a function of the Gaia BP minus LP color, we show the X-ray to bolometric flux ratio. This paper contains all the detail you want to know. I mean, I'm not going to go here into them. But just before closing, just a highlight of the fact that even in this small hard X-ray catalog has been studied extensively. This is a paper by a student of ours at MP, Sophia Waddell, who presented the identification of the AGN content of these 5,000 hard selected sources. Here is the redshift luminosity plane of the sample. The blue is this eROSITA hard compared to other hard X-ray selected sample like SWIFT-BAT. And the main property is main important thing is to understand up to which obscuration function eROSITA start being incomplete. And so we compare this hard X-ray selected eROSITA sample with the SWIFT-BAT AGN sample as a function of the obscuring column density. The black histogram is the SWIFT-BAT, and the blue is the eROSITA hard. And so you see that up to about 10 to the 22 centimeter to the -2 in column, eROSITA detect a very large fraction of the SWIFT-BAT sources, which are detected at much harder energies, and so are less affected by obscuration. But above 10 to the 22, our completeness drops significantly. Okay, this is the fast overview I wanted to give. As I told you, that Emmanuel will go much more into the detail of the cluster cosmology. Before I close, I just want to advertise a big international conference we are organizing in Garching in September from 15 to the 20. Registration is open. I think the deadline here is wrong. It should be May 30. So we have extended until the end of the month. So if you are interested, not only in listening to about eROSITA, but also in discussion about X-ray in the direction of future direction of X-ray astronomy and survey works, multi-wavelength surveys, please consider coming to our meeting in September. So these are my conclusions. eROSITA is the most powerful wide field X-ray telescope to date. It has completed 4.4 all-sky survey, and thanks to its large grasp, stable background, and observing cadence, we are opening up new parameter space for X-ray astronomy. And ERAS-1 release with the cluster cosmology you will hear about later marks the coming of age of cluster cosmology. And there are numerous science highlights from year one. I could only really scrape the surface, but the ERAS-1 is fully public, and you can find on this website also several dozens of highlight science paper that come with that. And with this, I will thank you very much and close my presentation. Thank you.
Thanks a lot, Andrea, for that very detailed and very broad overview of eROSITA. It's such an exciting data set. After your talk, I can't wait to go back and look at some of these things as soon as possible. So we'll go back to questions. Is there?
Maybe just 2-3 questions quickly. So first one is like, it's not a scientific question, but how long can eROSITA remain in safe mode? So second and third one, so I presume the website which you mentioned, right, that's presumably is that for the German half. So is there a similar point source release for the Russian half? And so third one is again about a point source one. So have any of the Fermi-led unidentified sources been seen in the ERAS-1 catalog or the corresponding point source catalog in the Russian half?
Okay, quickly, how long can we stay in safe mode? We don't know. We hope we can stay years. This was never planned to be so it's hard to know. But the instrument is safe by definition, and so apart from regular degradation by the cosmic ray interaction with the detectors, which is inevitable anyway, potentially you can stay there for several months, if not years. There is at the moment no plan, as far as I am aware, from the Russian half to release the data, at least not immediately. They have a very vague long-term commitment to do it eventually, but I don't think there is anything in the short time scale being prepared. But papers come out of their analysis, so some small samples are released with papers, so you have to just watch the archive. And sorry, what was the final question?
So Fermi-led unidentified sources.
Yes. So there is a paper that I didn't have time to mention from Meyer and Becker that did the experiment of searching for X-ray counterparts of Fermi identified sources, in particular searching for pulsar, X-ray emission from pulsar. So I think they have a sample of about 80 candidates with a probabilistic method, Bayesian probabilistic method. So each of them is associated with probability. They estimate that about maybe half of them could be newly identified pulsars. I think they haven't focused very much on Blazar or AGN. So I think the number for AGN should be even higher. But just look at this Meyer and Becker paper for more detail.
Hello. Thank you for the nice talk. I have a question. So, what is the criteria to identify the galaxy clusters, and also how to we measure the redshift of it?
Yes. I didn't really want to cover that because Emmanuel is I'm sure gonna go through it. So you just have to wait, what is an hour and a half or so. Quickly speaking, we have the luck of living in an area of intensive multi-wavelength optical surveys. And so we are using legacy DR10, which is a combination of the Dark Energy Survey plus a combination of a federation of DECAM GRZI imaging in the southern sky that covers essentially all our eROSITA DE extragalactic sky. And so we are using a method like the red mapper. We call it eROmapper. We go at the position of the extended X-ray sources and we search for overdensity of red galaxies to identify and get a photo Z for the cluster. And then we search, and then we complement that with spectroscopic redshift from the literature. And now we have started a spectroscopic follow-up program with Sloan 5 for both AGN and cluster. And eventually we will use Foremost to get spectroscopic redshift of 40,000 cluster. But at the moment, it's based on photometric redshift that use the red sequence, red mapper-like algorithm on the DR10 legacy imaging survey.
Thank you.
I had a question about the absorbing column plots that you showed. So I might have missed something, but did you say that there was not a consistency or some inconsistency between the BAT distribution and the eROSITA, or?
No, I mean, no inconsistency. I went quickly, I'm sorry, I'm sure I haven't explained myself, but let's say because BAT selects at 14 to 895 kV, BAT can detect much more highly obscure sources than eROSITA only detect up to 5 kV, right? And so the BAT histogram is considered to be almost complete or much more complete up to high columns. And as you see, because we don't have sensitivity above 5 kV, we see that we are very complete at low columns. Our blue histogram almost perfectly overlap the black. Then once you start going above 22, you see that the two diverge. And this is not inconsistency, it's simply incompleteness in the eROSITA because of the limited band pass of our detector.
Okay, thank you very much.
Of course, our detector is much more sensitive. So we detect many more sources at between 20 and 22 than Swift BAT. But we are systematically missing the most obscure ones. That's, I think, the message of this blog.
Do you have more questions in the room? Can I check with the online audience? Anyone have question? Please raise hand or you can unmute yourself and speak. Looks like no. So, Andrea, I will quickly ask one question about the spectroscopic follow-up, which
Yes.
you didn't say much, but could you briefly say what kind of spectroscopic follow-up you're considering and how astrometric error could be a challenge for the spectroscopic follow-up?
Yes, very good question.
Thank you.
So I'm sorry that I should have thought about giving the meeting, but okay. For spectroscopic follow-up, we have two programs we are heavily involved in. The first one is Sloan 5 as part of the so-called black hole mapper program. And Sloan 5 use both north and south telescopes. And with Sloan 5, we can get, first of all, we have targeting only sources after ERAS 3, only the first 3 all-sky survey, not the 4.5 we have. And then, of course, because Sloan is a much smaller telescope, we only go after bright optical sources. And the plan is to get 60% of the point sources that we detected at bright optical magnitude of 21st and so on. And then trying to get as many BCG and cluster members that we can. But the largest investment of resources for us is Foremost. So Foremost will start its survey sometimes in 2025, around summer, I think. And there are 2 programs in Foremost that will follow up of X-ray eROSITA source of the full ERAS 4 point something survey that we have, down to much fainter magnitude. So we are talking about 22.5 in the optical for point sources, and for cluster now I don't remember. But we are expecting to identify a very large fraction of the eROSITA point sources and clusters with Foremost. So this will be our main program, really aiming at high completeness. Of course, we only limit ourselves to redshift less than 1 for clusters members, because the legacy DR10 is probably not well suited to get accurate photo Z above 0.8. I think Emmanuel will tell you a bit more about that. But yeah, we have these 2 big programs. One is underway, relatively recently started, the Sloan 5, and Foremost will start about 1 year and a half from now.
Thank you. Thanks a lot, Andrea. Let's thank the speaker again.
Thank you.